code on this. Okay, so today we'll be looking at chapter 2, Chem in Context, Molecules of Life. All right, very important. And in terms of the molecules of life, how the class will progress, we're going to look at this chapter on the molecules of life. Once we are finished with this chapter, we'll entertain any questions. Then when we finish with that, we'll look at the worksheet from the last day, and then we'd move on from there. Okay, so that's how we'll progress for today. All right, so let's go. Just waiting for this from current slide. Just waiting for the conversion to occur so you all could see it from current slide. Come on. Okay, there we go. Okay, so today we'll be looking chapter 2. Last day, we looked at a number of things, including anatomical positioning and body directions and so on. Today we'll be moving on to the molecules of life. Very important. What is the most prolific substance in the body based on this diagram? What element occurs in the greatest amount in the body? Anybody?
Oxygen.
Oxygen, that is quite correct. Oxygen accounts for more than 65% of our total percentage, as shown here. Carbon is approximately 19%. We become aware of that if ever you see, have been to when somebody, is put in a crematorium, the remnants, the majority of that is actually carbon. What is left once everything else, all the gases and the elements are removed, you're left with carbon. Then of course you have hydrogen, nitrogen, and the other elements constituting all of the other parts of the body itself. What is the third most abundant element in the body? If I were to ask you that, what would you say? The third most abundant one.
Carbon.
Which one?
I said carbon.
The third most abundant.
Oh,
Hydrogen.
Hydrogen, yes, hydrogen, very good. I know you thought I said second, and I need to speak a little more clearly. Sometimes my voice gets a little muffled. So the third most abundant element in the body is indeed hydrogen. All right, so very important there in terms of, I would say for the in terms of this class, yeah, just to take note of carbon and hydrogen. Those are the major two that you will be expected to know. Okay. Okay. So what we're looking at here, this is known as the periodic table of elements. And this periodic table of elements, it was brought, or the person who arranged it in such a way was a Russian scientist named Mendeleev. And so if you think Mendeleev was the person who discovered it, what do you think they call the name of this periodic table? Is the blank periodic table. What do you think comes before blank?
Mendeleev?
Yeah, Mendeleev, yeah. So usually a lot of things when you look at in biology, you would find that the person's name is attached to it. Could you think of anything or any structure in the body in which has a person's name attached to it? Or any technique in biology that you look at? Staining, I don't know if you all come across that. Well, you'd come across that in microbiology, but there's a stain what they use to identify bacteria known as the Gram stain. And the reason why they call it Gram is not because of the weight, but because of the fact that it is indeed the person who actually did the first or discovered the type of ingredients to go into that stain. His name was Gram. So that is one of the things with biologists, you would find that, well, they spend so much time in the lab, so they put their names to it. When you look at in the kidney, you look at that in SNF2, there's a part of the kidney known as a loop of Henle. Yeah, Henry was a guy as well. And I know what some of the ladies saying was it only guys? Well, most of the times it was, because back then things were a bit quote unquote traditional. So the woman's place was in the home, whereas the men had time to do other pursuits, such as being in the laboratory and so on. It wasn't until, I would say, you had Madame Curie. She was the first person who was really recognized as a scientist, and she got the Nobel Prize. She distinguished herself both in the field of medicine and also in the field of physics. All right, so she was the first person, she was a French person and the first French scientist to be recognized. Ironically, her discovery together with her husband, they were working on radioactive material, and unfortunately that led to her death, right? She died from cancer caused by the radioactive material she was working with. Anyhow, let's go forward. Elements of life. When you look at this table, right, which is the periodic table, or sometimes you would hear it say, the Mendeleev's periodic table, the elements are arranged because there are certain properties associated with the elements. So it's just not randomly that they were placed like this, but there were certain things which are characteristic of these elements, which is why they were arranged in groups and periods coming across. Right? So for instance, hydrogen, lithium, sodium, and potassium, all of these substances here, they all have one electron in the outermost shell, hence the reason why they were grouped together. So when you look at this, the take-home message from this, you would see more of this when you look at chemistry. So I wouldn't get into the details, but just to appreciate the fact that in this periodic table, the elements are grouped because they have similar properties. Let's go forward. Okay, so chemistry. Properties of the elements. Let's look a little more into the properties of some of them. When you're looking at the structure of an element, the properties associated with it is one, there are certain charges, and these charges either is a negative charge, a positive charge, or sometimes some of the substances have no net charge associated with it. But the negative charges are usually the reason why certain elements have negative charges has to do with the fact that they possess electrons, and protons usually give a positive charge to some of these elements as well. Very importantly to note, when you have two substances or two elements coming together and they both have negative charges, what happens? Will they be attracted or will they move away? Anybody knows? So if you have two things with negative charges, think about it like two people. If you have two negative people coming together, what would happen? Do they usually stay together or do they usually move apart really quickly?
So they move apart?
Yeah,
Yes.
correct. You ever have some negative people, they come and they're talking, as they say, one sort of foolishness, the conversation doesn't go very far. And in a similar way, with electrons, when you have elements with negative charges, when they come together, yeah, they move away. They don't stay very long, right, together. So like charges, when we say like charges, if both of the elements have net negative charges, when they come together, they move away. If both of them have positive charges, so if the one on the left is positively charged, the one on the right is positively charged, if they are brought together, the forces push them apart. And similarly, if the one on the left is negative charge and if the one on the right is positive, if the one on the left is positive, the one on the right is positive, if they're brought together, they move away from one another, right? There's a force that actually moves them away from one another. So the take-home message is if the charges that are associated with two elements, one on the left and one on the right, if they are the same, when these elements come together, they're forced apart. But if they are unlike, right? So if it is that the net charge, they are unlike. So if one is positive and one is negative, you have a force of attraction, which it is. Okay. All right, atomic number and atomic mass. So the total number of protons associated with an element, this is known as the atomic number, and the atomic mass, this is determined by the total number of protons plus neutrons. Now the protons and the electrons, right? Let's look and see how do they, how are they located, or how do they exist within an element. So here we are looking at one particular substance here, an atom, and what is showing here, the proton, an electron, and a neutron. So within the nucleus itself, this is where you'll find your protons and neutrons, right, within the center. And then moving around it in an orbital, you'll find the electron. So if you could imagine, you could think about it like the Earth and satellites moving around the Earth out in space. The Earth itself then would be the same as the nucleus, and then the satellite that is moving around in outer space, this would be the electron. All right. Down here, for instance, what we're looking at, here you see the nucleus and you see the electrons. Quick question, are you all seeing the arrow that are moving about on the screen?
Yes, sir.
Okay,
Yes,
great.
sir.
Okay, great. Okay, great. Right, so here you have the nucleus, and these are the electrons which orbit the nucleus. Right, so very interesting. Now, if you look through a microscope, when you see these lines, when you see these things moving around like this?
No.
No, sir.
Absolutely not. In fact, you'll be very hard pressed to see anything. It doesn't look like this, look like this at all. They've recognized this by doing a lot of calculations. That's how they figure this thing out. But would you look in, do we have the capability to, let's say, look at an element and see it like this? Absolutely not. So this is just based on evidence. They've come up with this model, but we don't have the technology yet just to look in a microscope and see the nucleus in the middle and these electrons orbiting around it. No, but we could tell of their existence by doing certain experiments. It comes like if somebody is walking on the beach, right? When you look in front of you, you see footsteps. If you see the footsteps in front of you, what could you deduce happened? If you see footsteps, a set of footsteps, what would you say happened? Anybody? If you're on the beach, on the shore, and you look and you see footsteps on the beach, what would you say happened?
Somebody walked there before.
Yeah, somebody walked there before. Did you see the person? Absolutely not. But because what they left behind, you're able to deduce, well, the pattern of the footprint is that of a human. So therefore, more likely than not, this person walked there. Same thing with these, how they figured this out. They looked for evidence of what was left behind, and they figured out, okay, this is what the electron would have passed here. And this is where the nucleus is located and so on. Is that necessary for this class? Absolutely not. I just thought I'd fill you in on it. All right, isotopes. This is just another example. Atoms with the same number of protons, but different number of neutrons. I'll get a little more detail of this when we're doing the examples, but just appreciate this for now. Atoms with the same number of protons, but different number of neutrons. If we were to go back, we spoke about protons and neutrons located in the nucleus itself. So you have this special type known as an isotope in which the atoms have the same number of protons, but you have different number of neutrons, and that changes their overall weight. So one example is carbon. Carbon is usually written carbon-12, hydrogen, helium, lithium, barium, boron, carbon. It's 6 in the periodic table, but because of the fact that this number here shows that it has a differing number of protons from this one. And this one is known as heavy isotope of carbon, C14. And that is actually used for carbon dating things. All right, let's have a look now at the atom itself. So the atom, when you look at an atom in the periodic table, the elements which are arranged in the table from the first 20, from hydrogen, to calcium, from hydrogen to calcium, those are the first 20 elements. All of them show, when they are arranged in the groups usually behave very well in terms of showing common characteristics. Once you go past element number 20, it kind of gets a little shady, even though they are still placed in groups, and yes, they do have common characteristics, but the characteristics are not as well defined as the first 20. With the first 20, it's clear cut. After 20, things get a little shaky, okay? So first of all, let's have a look at these elements. First, let me ask this question. Anybody knows what is the name of this element we're looking at? So this is the shortened named here.
Helium.
How do you know it's helium?
Because I did chemistry in school.
You did chemistry, but it's written right down
Yeah.
here too. I don't know if anybody
Right.
noticed that. So one of
Yeah,
the things
right.
always remember in biology, use your eyes, yeah? So if you didn't know it was helium, always look around. And that's a very good point. It'll hold you good in life in general. If you see, when you're doing questions and you can't figure it out, you know, you're wondering what to do. One of the things, you always look all around and ensure you get all of the information available to you. So in this case, yes, it's helium. Helium is 2 in the periodic table. So therefore it has 2 electrons, right? 2 electrons which circling this nucleus, right? 2 electrons. And it has the number associated with it is number 2, helium, second. After helium is what? Let me see, my friend who did chemistry, after helium is what? Hydrogen, helium,
Lithium.
then
Lithium. Beryllium.
what you're saying? 5, where's number 6?
Carbon.
You know your stuff, well done, right? So here's carbon out here, carbon, this is the nucleus, and these are the electrons surrounding the nucleus. Do we have to get into any great detail for this course? Not really. Would you be responsible for a lot of chemistry? Not really, but it's good to have a background to appreciate a lot of the things which you would see in your professional career. So for instance, one thing that comes to mind is electrolytes. And anybody know what an electrolyte is? When have you heard the word electrolyte? Anybody? Wait, electrolyte. What comes to mind when you hear the word electrolyte?
Gatorade.
Gatorade. Yeah, thank you very much. Yeah, Gatorade. Right? Gatorade, that's in terms of one of the claims, it's an electrolyte. And what is an electrolyte? It's a big word. What does it do?
Supposed to give you energy.
Energy.
It gives you energy. Right, and I'll explain how it does that in a second. I spoke about it last day when we were talking about the nervous system.
Hydration.
It gives you hydration as well, yes, yes.
What is salts? The salts? Or
Thank
do you know
you.
what is salts?
Thank you very much. The salts, yeah. And when you look at salt, what is the chemical formula for salt? The same salt that is in your kitchen. It's 2 elements. One is sodium and the other one is?
All right.
Chloride, very good. Sodium chloride, very good. So which one carries the positive charge? If you put it in solution, right? The sodium carries the positive charge, Na. So you get Na plus, it loses an electron. And then the chloride ion gains it. So since electrons are negatively charged, when you lose a negative, you will go back to your math. When you lose a negative charge, you become more positive. And if you gain a negative charge, you become more negative. So sodium becomes positively charged, Na plus. And then you have the chloride ion, Cl minus. And all electrolytes are mainly salt. Salt is a major composition of Gatorade, of some of those rehydrants used for babies. Anybody remember the name of a rehydrant? If a baby has diarrhea or gastro, you know, and is vomiting or is it loses, yeah, he or she loses a lot of fluid, you then use Pedialyte. Oh, there's another one that it used to come in a foil packet, but of course, yes, now it's modern thing. They don't have that again. People will laugh at me if I say that. Right now, I understand now G-Sol comes in, they sell it already mixed, right? So G-Sol, and all, if you ever taste it, is nothing more than salt, is a fancy salt water, you know, that's all it is. So how does that help your body? As I mentioned, we look at that when we go on to the next topic, which is in the next 2 weeks, when we look at the nervous system. All you have to remember for now, though, the nervous system, it needs salt to properly function. And salt is nothing more than sodium chloride, and sodium chloride is nothing more than ion, sodium ion, and the chloride ion. So therefore, when you have diarrhea, salts follow the water out of the body. Whenever you lose water, you lose salt. That's why your sweat is salty, urine is salty, And I wouldn't advise it to taste it, but just take my word for it. Fecal matter, particularly watery stools, it is salty as well. You lose a lot of salt. You have to replace the salts in order that your nervous system functions properly. Your nervous system interacts with your muscles, which then in turn interact with your bones. Those three, nervous system, muscle, and bone, collectively are responsible for bringing about movement. That is why when you see you have diarrhea, and you're visiting the throne and you have your watery stools, that's why you feel so weak, because literally your nervous system isn't functioning well, and your nervous system is critical for the movement because it gives or provides a stimulus for muscle contraction. Muscle contraction is attached to bone, and then when you all those three interact, that's how you get to move. If one isn't functioning, namely nervous system, you just lie down there. Anybody ever had a diarrhea? Anybody?
Yes, sir.
Yeah, you know how you know when the diarrhea very bad? You know when you start to make
You
promises.
start to feel really weak.
Yes, that is true. But when you reach
Sir,
this stage,
and when you start a cold sweat.
yes, and when you start to make promises to Jesus, you ever reach that stage? Oh God, if you take this cross from me, if you do it, I promise I wouldn't talk back to my mother again. I'll be very good to my friend and them. I promise all my nephew and them, I will visit them. I remember the birthday. When you start to make, or to whichever deity you subscribe to, when you start to make them kind of promises, because you know it's very bad. And yes, it's associated with the sweating, the cold sweating. And overall, you feel weak. You have a very, you don't feel to move. And the reason why is because literally you don't have any of those ions which are critical for your nervous system. You don't have the salt. So with rehydrants, that's why it's important, not only when you have diarrhea to get water in, but more critically, get salt in. That salt is critical. And the change is incredible when you see somebody, literally looking like they're on death's bed in terms of being dehydrated within about 10, 15 minutes of taking in that rehydrant in the form of some type of electrolyte. They're up and about. It's absolutely incredible. You'll see this, of course, in your professional career as you go through, from year to year. All right, let's go forward. All right, so this is just speaking about ion, and we just spoke about it. When an element loses an electron, or if it transfers it to another substance, the ion now becomes positively charged. And coincidentally, we're looking here at sodium chloride. So with sodium, configuration 281. What 281 means? It means that the shells around them, for it to be stable in terms of how it exists, 2 is considered stable. 8, having 8 electrons in a shell is considered stable. So the usual configuration for the first 20, we're looking at 2, 8, 8, 2, right? Because, well, the outermost shell wouldn't have the full complement. So it'll be 2 in the first, 8 in the second, that's 10, 20, 10, 8 in the third shell, that'll be 18, and then 2 in the other shell. But the other shell could also contain 8. But just since we're just stopping at 20, we'll just say for our purposes, there are 2 in the outermost shell. But the 2, 8, 8 configuration, 2 and 8, 16, in the first 3 shells, it gives a lot of stability to that particular element. In this case, we're looking at sodium. Sodium has 11 electrons. So its configuration, how the electrons will be arranged, 2 in the first shell, 8 in the second shell or orbital, and then in the outermost orbital, you have 1. So in order to, what is known as for it to be stable, when it's stable, you want to move to a configuration where your shell is full. So for sodium, to attain stability, it would actually transfer an electron. If it transfers an electron, this outermost shell doesn't have any. So now it has a 2-8 configuration, which is considered stable. So it transfers that. When you look at chlorine, or the chloride, here's the chlorine atom. Chlorine now has a configuration of 2, 8, 7, right? 2 and 8, 10 and 2, 8, 2 and 8, 10, and 7 in the outermost shell. Now, if it gets an electron, 1 more, it would make 8 in the outermost shell. 8 is a stable configuration. So that's why with sodium chloride, what you have happening in terms of the formation, you have a transfer of the electron, such that this now becomes positively charged. It has lost an electron. This has become negatively charged. And now you have an electrostatic force of attraction between the two, between sodium and chloride. When you put it in water, that could be broken. And when it's broken now, you have the sodium ions and the chloride ions moving in solution. And again, sodium chloride, very important for the functioning of the nervous system. But just the take home from this in terms of what I want to highlight for sodium chloride in particular, when you hear the word electrolyte, electrolyte means nothing more than carrying a charge. All right, so electrolytes, a big name, fancy name, Gatorade, Pedialyte, all of those things, you hear them talk about electrolytes. All it means is carrying a charge. And how does it carry a charge? All it's doing is carrying salt water in solution. And in solution, you have these charges, sodium and the chloride ion charges, sodium Na+ and the chloride ion Cl-. That is what is present in those things. But looking at it from a very simplistic perspective, all it is salt water solution. That's an electrolyte. A very good definition for an electrolyte is a salt water solution, because a salt water solution carries charges. All right, ionic bonds. So we just mentioned this, right? When you have the transfer of the electron, it becomes positively charged. When you have the acceptance, it now has a net negative charge. And because of the positive and negative, unlike attracts, so now the sodium and the chloride ion, they're attracted to one another. And what we're looking at here is a salt crystal with sodium and chloride ions. Of course, when you add the water, it breaks those bonds and it releases the chloride ions and the sodium ions in solution. All right, covalent bonds. Just to appreciate the fact, covalent means sharing. So when you're looking at hydrogen molecule, which consists of two hydrogen atoms, each one having one electron in the outermost shell, to attain stability, that is to attain two electrons in their first shell. That's a stable configuration when you have two electrons moving in your first orbital. So what they do, they share it. So if they share now, it comes like, okay, yes, I have one, but I have the other one at some of the time. So in a way, yes, it's like a borrowing one. So some of the times this electron will be over here, some of that time will be over here as well. But ultimately, I have a share of two. So this gives me a certain degree of stability. And that sharing of the electron, so that both atoms attain stability, that is known as a covalent bond. So you have covalent bonds involving one electron. You have some which exist like in oxygen, in which they share two electrons. When you look at oxygen, oxygen's configuration is oxygen is number 8 on the periodic table, has a configuration of 2,6, which means 6 electrons in the outermost orbital. It needs 2 to get that configuration of 8. 8 is considered stable for the outermost shell. So what it does, it could hook up with another oxygen and borrow 2. So if it borrows 2 or shares it, so now you have this oxygen, it's sharing 2 electrons. So it now has a total of 2, 4, 6, 8. Relatively stable, has a stable configuration there. So O2, which consists of 2 oxygen atoms, that is stable because of the fact you have 2 covalent bonds existing between the 2 oxygen atoms. All right, I know some people might be saying, ooh, that's something very in-depth. So just appreciate, this will be the only time you'll actually be looking at these concepts, right? So just appreciate it for what it is, and you wouldn't be looking at it again, fortunately, okay? Now, polar covalent just means so you have these 3 elements. You have hydrogen atoms and you have the oxygen. They are going to share. Oxygen has 6 electrons in its outermost shell, hydrogen 1, 1. So what happens is one of the hydrogen will share one of oxygen's outermost electron and the other one would share. So now you have 2 hydrogens and 1 oxygen. And when you have 2 hydrogen and 1 oxygen, what molecule does that form when those 3 atoms come together?
Water.
Water. How do you know water is formed? Based on what you're looking here, right? Because it marked right here, water molecule. Always remember to use your eyes, but water is quite right. But the thing is this, oxygen is considered, because it has so many electrons, it is slightly negative, the overall charge when compared to hydrogen, which only has one electron in the outermost shell. So while they are sharing the electrons, most of the electrons, the time will be spent over on this side. So it comes like oxygen is pulling these electrons over to this side. And because it is pulling all of the negative charge, remember when you lose a negative charge, what happens? You become slightly positive. And that is why when you look at water molecule, it is known that the water molecule is slightly polar, where the oxygen side is slightly negative, because of the fact that oxygen is electronegative and will keep or pull its electrons, the electrons that they are sharing will keep them most of the time over on this side. Whereas the hydrogen, well, it only have one, so while the pull is over there, it comes like if it has lost an electron. So in losing that electron temporarily, as it moves over in this orbital here, it has a slightly positive charge. When you lose a negative, you gain a positive charge. So water is polar. It has both a negative and a positive side to it. Okay. We looked at some of the elements. We looked at their arrangements in the periodic table. They're placed into groups. These groups are important because in a group, it has certain characteristics associated with it. Now let's move on to functional groups. Now, certain substances, they have what are known as particular groups of atoms or elements. And because of that, when they have this grouping, they have similar characteristics. So let's look at some of these and let's see if we could actually name them. So OH is a hydroxyl group, right? OH. Carboxyl, COOH, and where would you find this group? For those who did chemistry, where would you find what group of substances you'll find OH in?
Organic.
Organic substances, yes, yes. Right. What else? Alcohol.
Yes, sir.
Right. Alcohols, you'll find them in COOH. Carboxylic, you'd find this in what? COOH.
Acids.
Right, acids. It is acids, right? C double bond OH. Right, so this is the acidic group. NH2, this is an amino, and incidentally, you'll find both of these amino and the acid, right, present and in these constituents of proteins, and that's why they are called amino acids, because you have an amino group, NH2, and you have an acidic group, C double bond OOH, present in these compounds. So all amino acids, they have both an amino group and an carboxylic acid group, and that's why they call them amino acid. Part of it is an acid, part of it is an amine group associated with it. And this is the other, well, this is an alcohol functional group, hydroxyl, and this is a unique part of the molecule up here. Right, methyl, just a CH3, phosphate, PO4 2 minus. This becomes important when we are looking at DNA, right? So it has DNA, has a base, and it has a phosphate group. There's a base here, adenine, attached to the molecule. And of course, in the middle, you have a sugar, right? So sugar, phosphate group, and a base. That is all repeated in a double helical structure known as DNA. We'd look a little bit more of that when we're looking at respiration. Oops. Okay. Ions, acid and bases. Just a note, just for the definition, acids, they give or they donate protons, and bases, they're proton grabbers or they accept protons. So acid give protons away, bases accept protons. How would we remember that? Anybody has a way in which you remember that? That acids, they give off protons, but bases, they accept protons. How would we remember it?
So I would say, seen as acids give off protons. Acids are negative stuff, kind of like, how acid burn you, and seen as bases grab the protons. Bases like positive stuff, seen as how like you would use a base to make something less acidic, if I'm making sense saying that.
Yeah, yeah. And whichever way, you know, helps you remember, that's fine. It makes a perfect amount of sense. Once it, all that matters, it makes sense to you. Yeah. And that is good. That's a very good analogy there. All right. So we saw water is slightly polar. Now we're looking at intermolecular bonds. So here we're looking at water. And all you have to remember is in the case with water, so because of the fact that we have water, oxygen and hydrogen, slightly positive charge, slightly negative charge. So another water molecule, slightly positive, slightly negative. So because of the fact that you have difference in charge, you have a negative over here and a positive, you have these weak bonds, which are known as hydrogen bonds that exist between the water molecules. And that gives water its unique properties, the hydrogen bonds that exist between the molecules themselves. Now, these bonds could be broken and the molecules liberated when you apply heat to it, right? So you do have a breakage of the bonds, and that's why you then have a change in form. It changes from a liquid into a gas because of the fact these bonds are broken. All right, solution. What is a solution? Well, when you speak about solutions, you have solutes and solvents. So the solute is what you put into it. The solvent is the substance that dissolves it. And the solution is what you have at the end. Let me ask this question. I'm making lime juice. Everybody here like lime juice? Anybody do like lime juice? Good. So I'm making lime juice. I have the lime, I have water, and I have sugar. So at the end, I want to get lime juice. Could somebody tell me what is the solute, what is the solvent, and what is the solution?
Sugar is the solute.
The sugar is the solute, right? And it can
Because
also
it
add you the lime.
dissolves.
Yeah, well, the lime is, I hear what you say, the lime. Yeah, go ahead, the sugar. What is the solvent? So what dissolves it? What dissolves the sugar?
The water.
The water, right? And what is the solution at the end of it all?
The solution is everything comes together. Everything
And what is
comes
that?
together.
Lemonade.
Lime juice.
Is lime using rough lemon? I see the price in the market and I nearly jump dead. So if we were using lemons, correct, we get lemonade at the end. If we're using lime, we get lime juice, right? So quite rightly, the solute, what is dissolved, that's the sugar. What is doing the dissolving, which is the solvent, would be water, and the solution at the end is lime juice. If you're using rough lemon, the lemon does actually, in a way, you could say is part of the solvent because it's a liquid and it does help to dissolve the sugar. But it'll be the same thing. Sugar will be the solute. The water will be the solvent, and the solution at the end, which is the lime juice. When you mix it up, that is the solution, right? And that is very important. Remember that analogy. You might see it again in a question, okay? But that's how you're actually, it's a nice way to remember solution, solute, and solvent, right? So solute, always remember, is what is dissolved. So nice way to, solute and sugar both have a U in it. You know, if you were to get your mind around that, because it's easy sometimes to mix up the terms, you know, which one is the solute and which one is the solvent. I just remember, like, sugar has a U and solute has a U. So therefore, when you join that analogy and make it juice, remember solute is the sugar. All right. Okay. Enzymes. Are enzymes important? If I were to ask you that question, what would you say? Are enzymes important? Okay, that was a rhetorical question. The answer is yes, it is important. Let me ask this other question. What would happen if we didn't have, I'm going the wrong way. What would happen if we did not have enzymes? Very simple question. Sorry.
No chemical reaction will take place.
Yes. And why are enzymes particularly important? They alter what part of a chemical reaction? One word, 5 letters, it begins with S and it ends in D. And it rhymes with seed.
Speed.
Yes, yes,
Speed.
very good, very good, very good. Speed, it alters the speed of a chemical. Excuse me. Speed of the reaction. Have a bit of, excuse me 1 second. Correct. So it alters the speed of a chemical reaction. Usually, does it speed up or slow down the rate of a reaction in our bodies? When we look at the majority of enzymes, what do they do? What do you think? Would they speed it up or slow it down? Yeah, very
It
good.
speeds it up.
Yeah, it speeds it up, right? It usually speeds them up. It could slow them down as well, but usually it speeds it up. And when we want to talk about rate of a reaction, where's a nice experiment to look at rate of reaction? Everybody familiar with Andrews, Andrews or Enos?
Yes, sir.
Right. A nice way to look at rate of reaction is to take a glass of cold water, icy cold, right? Freezing cold, cold water, and then take a normal room temperature glass of water, right? Put it there. Open a Enos, a pack of Enos, throw it in the cold water. Open a pack of Enos, throw it in the normal room temperature water. In which one would you have a reaction taking place first? The one with the cold water or the one?
Water.
Have you ever tried that experiment?
Yes, sir.
Anisha, you should try it. And you would see, yeah, the one at room temperature, it will start a bubble and fizz, you know. It will start a bubble and fizz. Whereas the cold water, it stays a while and it moves very slow. You'll start to see bubbles coming up, but very slowly. And that's an example of looking at the different rates of reactions. So what enzymes do? They speed up the rate of a reaction. Because if not, if that wasn't the case, certain reactions in your body associated with metabolism, it would take forever to happen. That's why enzymes are very critical in the body itself. So some of the metabolic reactions, one of the more important one, synthesis, right? Synthesis type reactions, in which this example shown here, using a tree, right? You have the sun's energy. It is synthesized, the air and water synthesized to form what? Complex sugars. Sugars are nothing more than a rearrangement of carbon, oxygen, and hydrogen, and that's what a tree does. So when you build up, right? So building up is known as anabolism. And when you break down, that is known as catabolism. So catabolic reactions, they release energy by breaking bonds, whereas anabolic reactions, they combine atoms into larger ones, incorporating the energy in the form of chemical bonds. All right, so very importantly to take note, when you have anabolism occurring, the energy is locked into the bonds. And what do we do when we eat? We just break those bonds, right? Give off carbon dioxide and water, and that bond energy is used to power our muscle contraction and different things. And one of the unique things about humans, the energy currency is in the form of 3 letters. What 3 letters are they? We only use one type of energy for all the activities in the body. 3 letters, what are those 3 letters?
ATP.
ATP, yes, adenosine triphosphate. We'll look at that a little later on. But all of the energy that we use in our body is in the form of ATP. Now, is that important? Or could you see an advantage of just using one type of energy as opposed to using different types of energy? What do I mean by that? Let's say you wanted to wiggle your nose, and now you have wiggle your nose energy. Let's say you wanted to move your little toe. Now you have little toe energy. Let's say you wanted to stand up. You have stand up energy. Now, could you see an advantage as opposed to having those energies? You just have one type, ATP. And ATP, if you want to wiggle your toes, you send down ATP. You want to stand up, you send ATP to the muscles for you to stand up. Could you see an advantage of just using ATP as opposed to having a whole set of different types of energy? Anybody?
I would have to say not really an advantage, because if you only have one type of energy, it's more things for your body to do. I won't be able to do different tasks at the same time.
Oh, you can say that again because I think you answered the question. Say it again. Yeah.
How I think about it, I wouldn't say it's much of an advantage, but kind of a disadvantage. If you're using one type of energy, you won't be able to share it up and do multiple tasks. Where you have different types of energy, more than one type of energy, where you could do different tasks, wiggle your toes, raise your hand at the same time.
Okay, I got you. All right. Okay. Let me see if I can draw another parallel. I hear what you're saying, and I like your logic. Everybody here, I only draw an analogy to High Street. You have to excuse me. I spend most of my life down in San Fernando. All right. Like say you go to Gulf City Mall. All right. Everybody, or you go to a mall in general. Now, is there an advantage in using a links card? Let's say if you go to on the food court to buy KFC, and then your little son or daughter pulling you and say, no, mommy, or no, daddy, I want some Royal Castle. So now you could go over by Royal Castle and you could swipe your card. And then now you go downstairs and you're buying some clothes, you go into the clothes store, you swipe your card there. All right. And then let's say you go in and you see the you're passing by a sweet store and you want to buy some sweets. So you go in and you swipe your card. All right. So you're going to 4 different stores by using the same card. Now, suppose now you could only buy Royal Castle with Royal Castle card. You could only buy KFC, let's say with a KFC card. You could only buy sweets with I don't know, whoever the name of the store, we'll call it sweet card, right? Now, what would your wallet look like if you had to have a specific card for everywhere you go, as opposed to just having a links card, which would be more convenient?
Very bulky.
Links card.
Having a links card.
Yeah, and you see, so that is the advantage why I wanted to show, with the body having just one currency of energy. So the energy currency of ATP, think about it like a links card. When the time comes to make energy, everybody knows the only thing we're making is ATP, only ATP. Now imagine how tricky it would be. How would they know how much nose hole muscle energy to produce, how much little toe energy currency to produce, how much stand-up energy currency to produce? It'll get complicated. Or let's say even if you made stand-up energy and let's say a little toe scratching, you have now to convert it. It would make things a lot more complicated for the body if it had to keep converting, interchanging between the different types of energy. Or 2, spending a lot of time figuring out which one I should make. And even in doing that, let's say it had to make, let's say you eat an apple and you have to make 50 different types of energy, stand up straight, bend down energy, all of these different types of energy. It would make it very complicated. And once you start to add complications to a machine, your body is nothing more than a machine. Right now your brain have to think harder. It has to come up with more processes. And as we're well aware, when you have more processes, things start to get complicated and you start to get more and more errors. So for efficiency, that is one of the major reasons for efficiency. You have one type of currency in your body for energy, ATP, and it makes it a lot simpler for the body in terms of both making it and also utilizing it, because it's accepted in everywhere, all the stores in the body. Is accepted in Royal Castle foot, is accepted in KFC nose hole. Everywhere you go, it is accepted. That is okay? That concept?
Yes, sir.
Yes, sir.
Right? And that explains why it's very efficient to just have one type of energy over the others. All right, remember that one, you might see it again. All right, yeah, go ahead.
Give us that as a question. We could put the example, right?
Yeah, of course. Explain it in your own words. That's one of the things I always encourage you. Whenever you get a question, especially with me, and you can explain it in your own words. Let's say for some odd reason there are big words associated with it and you cannot remember, break it down. Always remember that. Always write something. because one of the things, I'm not psychic, so I wouldn't be able to read a blank page. So always write something, write it in your own words. Once I understand where you're coming from, I always try to put myself in your position. You would get either partial credit or you might surprise yourself, you'll get full credit. So most definitely always write something, but please never leave a blank page. Oh, no. All right, good. Let's go forward. Okay, so inorganic, chemistry of things. Organic, as somebody rightly pointed out, organic just means they contain carbon and products of metabolism, namely oxygen and water, hydrogen. Inorganic, they're found in living and non-living things, contain no carbon atoms, except for carbon dioxide. So that's just the difference between the two. Organic, carbon, oxygen, and hydrogen. Inorganic, in particular, it doesn't contain carbon, with the exception of carbon dioxide. Dehydration. So here it is, we're looking at reactions. Dehydration. What does hydration mean? When we say something is hydrated, what substance is associated with hydration? When you hear the word hydration, what comes to mind?
Water.
Water, yeah. So D means, when you look at words, it means like not or no. So dehydration means what? You're removing
Loss of water.
Yeah, no water or not water, right? So in other words, you're removing water. So a dehydration synthesis reaction, you're removing, you're building up water, but you're removing it at the same time, right? So taking out water from the substance in terms of dehydration. And what is dehydration used, right? When you think about it in cooking, dehydration is used not only as a cooking, is used mainly as a preservative, right? And preservative, you could preserve meats, you could preserve fruits by dehydrating it in particular, and you remove the water. Let me ask this question. I answered this last time. Why are you removing the water? Why is it that when you remove the water, something will stop decomposing? Anybody can answer that question? In your own words, why it is when you remove water, it will stop decomposing? Because water, go ahead.
Water could attract bacteria.
Right, go on. Yes, go ahead.
So yeah, we'll stop there.
Oh, that's where it's stopping?
Yeah, because I didn't think about it that far.
Much. Somebody wants to pick up? So you're right.
No
So let's
reaction
start.
is taken here.
No reaction. I like how you're thinking. So you were right. So when you're thinking of decomposition, decomposition is usually associated, let's say, with bacteria and other microorganisms. And these things as well, their reactions take place in a watery environment. It's critical. If you have no water, none of those reactions will take place. And one of the examples we gave last day in terms of a reaction which takes place in our body is glycolysis, which is the breakdown of sugar and to give you carbon dioxide and water, and most critically, energy. Right? So that's one example, and believe you me, that exists in a watery environment. If you pull out the water, glycolysis wouldn't happen. And in a similar way, those bacteria, they have a whole lot of reactions that take place in a water environment. Pull out the water, wouldn't happen, and ultimately what would happen to them, they die. And when they die, they could no longer, let's say, decompose things by consuming the tissue and releasing waste product, which has a foul smell. So therefore, that's how it's preserved. And both salting and putting things in sugar, as you're well aware, or putting it in alcohol, right? All of those things, they stop the process. Alcohol is it actually dehydrates things when you use alcohol, and is also a very good preservative, alcohol. Okay. We're almost there. Fight them. So dehydration, right, removes, and the opposite of dehydration is hydrolysis. Hydrolysis inserts water. So dehydration, you're removing, hydrolysis, adding water. That's just a take-home message. And this is just showing you with a dehydration synthesis, you have the formation of water as a waste product. With hydrolysis, you're adding the water to form a new substance. All right, so let's take note. Dehydration synthesis, at the end of it all, water is formed, whereas with a hydrolysis, when you have the reaction, you're adding the components of water. So here, in terms of a short polymer, water consists of OH and a single H. OH is added to one, hydrogen is added to another one of the substance. Take home message: dehydration, water is formed. Hydrolysis, you remove the let me say that again. Dehydration, removal of water. So here it is, you have the components of water taken from the two reactants. So water is formed and is given off. So ultimately these are dehydrated. And when you're looking at hydrolysis, what you have happening is you have this polymer and you're adding the components. So to form two new substances that have the components of water in them. So in essence, one is just the reverse of the other. This one, dehydration, you're forming water, and then you reverse it, you get hydrolysis, okay? Acid and base. For the purpose of this class, acid and base has its properties when you look at the pH scale. And if I were to ask you, what is the pH scale? What would you say? It's a measure of what?
Acids and bases.
Yes.
The potential of hydrogen, I think it means.
Ooh la la. You hit the nail on the head. Yes, Amira, thank you very much. Right? So it's a measure of the potential of hydrogen. That's what the pH stands for. Right? And it's just a measure of how acid or alkaline. So you have two parts of the scale, acid and alkaline. And what is in the middle of the scale? At neutral.
Neutral.
Water. Thank you very much. Right? Water, pure water, is at a pH of 7. So if you notice, there's the alkaline side, it goes from 7 to 14, and the acid side goes from 7 to 0. Let me ask you this question. What is more acid, lemon juice or urine? What would you say?
Lemon juice.
Lemon juice.
Right, so if you look here, you see lemon juice. And what does that tell you about the numbers on the acid scale? Which one is stronger? So if a substance, if you're looking at something has a pH of 2 or something has a pH of 6, which one is the stronger acid based on what you just said?
What is that 2?
Correct. Very good. Yeah, very good, very good. So one of the things to remember is this. 7 is the neutral, and just draw an arrow going this way and another going away from the 7. The further away you go, the stronger you get, right? So for an acid, if something has a pH of 2, it is stronger than something like 6. And similarly, if something has a pH of 13, it is a stronger alkaline or base than something that has a pH of 9. So if you're looking here, bleach. Everybody familiar with bleach?
Yes, sir.
Yes.
I don't know if you're aware, bleach is the best cleaner out there. You know, it have all kind of things they show you on TV, Floralene, and all the other disinfectants on the market. Which other disinfectants it have? They smell nice.
I think Lysol.
Lysol, right? Pine Sol. I'm trying to remember this one. It have one like with a Spanish name. And it's
Fabuloso.
Oh, sí, señorita. Oh, yes. Fabuloso, yes. Right, all the different colors and so on. Yeah, right. So that is very good. It's very nice and so on. But nothing could beat bleach when it comes to cleaning. And if there's one place I would tell you to spend a little bit more money when you're shopping is on bleach. What's the best bleach out there? Bottom line.
Clorox.
Clorox. Clorox. And I am not endorsed by the Clorox company or any other company. I'm just saying this as a matter of fact. Bleaches are not the same. So when you see it have a bleach for $5, you know, and it's a big thing, and you look at the Clorox, it just has a little, there's a reason for it. The active ingredient, which is the hypochlorite, it is higher in Clorox than in any of the other bleaches. So which is why if it's one place to spend a little extra, I don't think tight, believe you me, right? Is to buy Clorox whenever you are buying bleach. But if, of course, if you can't, if things seriously tight, well, what you do, you'll buy whatever, you know, whatever other bleach is available. But if you could, always buy Clorox as the cleaner because it has more cleaning agent, the hypochlorite, than any of the other bleaches. All of those bleaches available on the market, not the same. So which is why you might see a big container, you know, for $5 and Clorox, a chunky little container for $15, but it's worth your while. And always remember that much. It have all of those fabuloso, blah, blah, blah. If you really want to keep it straight, bleach. And why I tell you that, even in the labs, right, we use bleach. And you know that because you use it as well. Use bleach as it's an excellent disinfectant, bleach. So always remember that in terms of cleaning up, for cleaning all through your home, from the toilet straight to kitchen counters, everything. It's a very good. Just mix it in the proportions that they tell you, and you'll be good. All right, it's much better than all of those. Yes, Fabulous, and all of them have a good smell. Oh, lie. But always remember, Clorox, bleach, diluted in the correct proportions is really good. Yeah, go ahead. Question. Go ahead, Lucy.
Yes, so I never know it had a difference between bleach and Clorox, so now I learned something new this morning.
Yeah, in terms of cleaning agent,
buying bleach.
You just say any bleach, it don't make a difference, and you probably so wonder why it is. All these people so wicked that they put in the price of Clorox so high, you know, and so anyone that you pick up, no, it has a big difference, and it has to do with the active ingredient in it. So it has different grades. Oh yeah. In terms of that hypochlorite, the concentration of that hypochlorite is different. It differs from bleach to bleach. And you could do it by yourself. When next you go to the grocery, look to the back of bleach, turn around the bottle and have a look. And look for hypochlorite, which is HCOL, I want to say, which is a measure of the concentration of the chloride ions. And you'll see, look at it for Clorox and look at it for the others. And you'll notice that Clorox has the highest percentage of all of them. Yeah, okay, let's go forward. Mention that, right? pH scale. So we didn't mention that. So bleach, so do take note, moving away becomes stronger, moving away becomes stronger. So 1 is stronger than 6, 13 is stronger than 8. We good on that? What is the pH of blood? Just about what, 7.4? Can I hear an amen?
Is a range 7.35 to 7.45.
What would happen if you go outside of that range? Let's say if your blood were to go to 8, what would happen to you? ... Or you'll be dead. You'll be dead. Yeah. You'll be speaking with the ancestors very quickly. If it goes down to 6, what would happen? ... You'll be dead. You'll be dead very quickly, which is why the body has an inbuilt, and we look at more of that in SNF2, the body has an inbuilt buffering system. Yes. Somebody had a question. Mm-hmm.
Yeah, so as you said that, the thing with the blood,
Mm-hmm.
would that explain conditions like respiratory conditions?
Oh, yes,
and
it does. Respiratory acidosis. Mm-hmm. Yeah, that is why it's critical. It can't go past, well, the range has said 735 to 745. You can't go further outside of that. In fact, 7.6, if it hits 7.5, you'll start to have serious difficulty in your body. And if it remains like that for about half hour to an hour, ... you will be gone. So that is why we're critical with blood. Measurement of blood gases is important. And fortunately for us, however, we have a mechanism to keep it in check. We have blood buffers, and we have a system, an inbuilt system that keeps it between 735 and 745. But if for some odd reason that fails, and it's a backup, when you look at both respiration, you recognize that how it is that the body actually keeps it in check, and also blood buffers as well. So you have more than one system. Plus, as well, you have detectors in the body that picks up any changes, adverse changes, and it alerts the body to do certain things to bring it back in check. So you have a number of mechanisms devoted just to keeping that blood between 735 and 45. So it's highly unlikely all of them fail at the same time. It's highly unlikely. But if it does, if they all fail at the same time, yeah, you'll be speaking with your ancestors within the hour, most definitely. Yeah. Okay. Yes, Lucretia, go ahead.
Yes, so I watching that the battery acid, right, is how much? 1.
Yeah.
And the, let me say the household bleach is how much? 12 point something?
Mm-hmm. Yes.
Which one is more dangerous?
Both of them, if it is you consume it, if you drink it, that's what you're thinking about?
Yes, exactly.
Both of them are dangerous. Which one? I don't like how the direction this question going in. Next thing tomorrow, when I look at the Guardian, I look at the Guardian.
pH scale now. I'm watching the pH scale and I'm thinking about some, stuffs. Well, not dangerous stuffs, but which one could be more dangerous?
I was just teasing you. Both of them burn by dehydration. They remove water. So I don't know. I'm sure some of you all might have experienced it when you're washing and the bleach fall on your hand. If you just point it, or if you're pouring it out into on your clothes, some people like to play saga boy or saga girl, and you pour the bleach directly into the water, and then you just put down your hand and mixing around the clothes, and you sometimes feel it warm. I don't know if it ever happened to you. You'll feel like a warmth on your hand. Ever happened to anybody? I know because obviously I do it because I can talk from experience. What is happening there? Bleach is, both of them, they're very good dehydrating agents, and that's how they burn. They pull water. So which is why it's always advised, to in terms of mixing, to add the bleach to the water and not the other way, because if you do it the other way, it could splash on you. All right, but they're very good dehydration agents. Neither of them, both of them are considered lethal weapons. So that's another thing, we have anybody here who like to fight? Or anybody here who like to make ruction? I see hand, Charles, I'll come into you shortly. One of the things, if ever you're in a grocery, one of the aisles never to get into a fight with somebody is the laundry aisle. Yeah, you don't want to do that. Get in a fight with somebody in the marshmallow aisle, the sweetie aisle, let them pelt you with marshmallow, you would live. But if you get in fight in the laundry aisle, that's a problem because they could throw bleach on you. And I'm sure you're well aware, it has happened in the past, right? Where somebody get bleach thrown on there, it could blind you. If it hits you on your eye, right? It could blind you. And one person comes to mind, there was this NFL footballer. I don't know the details of it, but his mother actually got blinded because her significant other, there was some marital dispute and he threw bleach on her, and it splashed in her face. And she lost her sight because of that, right? So always remember, choose your battles, but never battle in the laundry aisle. Yes, Mr. Charles, go ahead.
Yes. I was just thinking though, like how we have 7 as a neutral number here on the scale, right? So anything in the direction of blue, if I could say it like that, right, is outside of 7 is still not like a healthy situation.
This is just a good question. So if you're look at it from this perspective. If you're looking at acids, the closer, let's say around 0, close to 0, as in hydrochloric acid, this is the strongest acid you could get. As you move across this way, so if you notice the color is getting fainter and fainter, the acid content drops. So it drops and it gets weaker. So from an acidic perspective, you would say that soap is a very weak acid, or even cleaner, they are very weak acids. But over on this side, this is where base. So this is the strongest acid, this is the strongest base. So as you become more, if you were to think about it this way, you become less and less acidic, you're becoming more and more basic. So this is the strongest base here. And conversely, when it goes down, when the pH of this base goes towards 0, it's considered to be a very weak base. But while it is being a weak base, it could be considered a very strong acid on the scale. I don't know if I explained that right to you. I don't know if
I get that. I get that.
yeah. But does that mean, you know, so for instance here, when you look at bleach, bleach is considered a weak acid, right? Because look at it, probably on the acid, you'd say it's a very weak acid, but it's a very strong base. So could it do damage as was mentioned before? Yes, it could do damage. It could do a lot of damage, right? But there's just a measure. It's just a measure of the hydrogen ion concentration, right? So in terms of high hydrogen ion concentration, these down here have a very high ion concentration, hydrogen ion, but as you move away, it becomes weaker, the hydrogen ion concentration. And the hydroxide ion concentration, which is the OH minus, it becomes stronger. So hydrochloric acid, highest hydrogen ion concentration, whereas sodium hydroxide on this side has the highest hydroxide ion concentration of the OH minus. I don't know if that helps. So, but in terms of pure classification, because water is considered neutral, on this side of water is considered acidic, and on this side is considered basic. So water is like in the middle. So water is considered neither acidic or basic. It's just like the midpoint between the two. That's okay? Okay.
Yes, that's good.
Okay, thanks. All right, let's go.
You have a class now?
I'm coming out there. I just
want to know.
Okay, let's go. So there's just a case here. So this is back to what Charles was asking, right? If you consume lemon juice, what would happen? Hydrogen ion enters the blood from the intestine, and too many hydrogen ions. So what happens, right? And some of us could identify with that. You know, when your stomach feeling acidy, and what do? You take Andrews for it, which is bicarbonate ions. Why is it you put bicarbonate ions? Anybody with who did chemistry? Oops. Anybody who did chemistry could help me out? What type of reaction, when you have an acid reacting with a base, what does it react to produce? A neutralizing reaction. So acid reacts with a base to produce salt and
water.
Thank you very much. Yeah. So that's why when you see your stomach feeling acidy, right, it's very good to take bicarbonate, sodium. So if I don't have Andrews, could I take sodium bicarbonate? Of course it could, right? Or if not, you know, use that. What else?
Baking soda, water, bicarbonate.
Baking soda. Yeah. You could actually take that, you know, to neutralize it. If you do have your stomach burning, if you eat a green mango and your stomach burning, yeah, bicarbonate of soda will work. Anybody else knows of any other remedies for stomach ailments? Let's say if you have, yeah, very good. Oh, you're a sharp boy. Very good.
Baking soda and water.
Yes, baking soda, because it's a base, and the reaction is acid reacts with a base to produce salt and water. It's a neutralizing reaction. So in other words, then you're removing the acid, you're breaking it down and converting it into something that is relatively harmless, which is salt and water. So that's the major reason why when it is you see have an acid stomach, you take Andrews. Andrews or Enos, the major component of it is carbonate. Same thing that you would find in baking soda, carbonate ion. So you have a neutralization type reaction in your stomach to neutralize the acid content. Good. And let me ask a little something slightly off. If you're having diarrhea, what's the best thing to take? Something that you find in your kitchen. Anybody?
Flour water.
What you're saying, you hit the nail on the head. Yeah. I don't know if everybody are aware of that. Flour and water is about the best thing you could take, you know, when it is you do have a diarrhea. I know a lot of people will Pepto-Bismol and all the different things. Yeah, but mix it. Explain how you take it, the flour and water, what consistency and so on you use. Go ahead.
So well, I never mix it for myself from what I mixed it from, but it was just kind of watery. Not too watery, but it was watery.
Yeah, so just mix in a sense, thanks very much. You just mix it until it's a little watery, such that you could drink it. And that's the best way. Yeah, once you do that, it's very good. Or Lomotil. Okay.
Yeah, Lumotil.
I'm not familiar with that one actually. Lomotil. Lomotil, that's something you take for your stomach as well for diarrhea.
It's to stop the diarrhea, and you'll take Dulcolox to induce diarrhea.
Yeah, Dulcolox, yeah, that's a stool softener. Yeah, we know about that one. That's particularly, I know some people, on that topic, let me just touch on something else and then move off. If let's say you have a young child, your little baby, your poo-poo, and you know he or she having trouble going off, and you know you see them sweating, and they're not coming off, what would you do? You know, and you see the feces, it's hard. What do you do?
So you give them as much water or some, let's call this thing, oh gosh.
Gripe water?
Gripe water?
No, it's oil it does have. Gosh, this oil, boy.
Castor oil?
Yeah, well, castor oil and paraffin oil and stuff like that.
Okay, right, and that actually, that does work, yes. What else you would do? If you're a mother and you're watching your child grimacing, you know, and sweating, what you'll do? And you know,
I want you to give me ripe bananas.
Ripe bananas, right? That would work. What else would you do to stop it from happening? Well, not stop it, but to ease the discomfort. I remember with my brother, what my mother would do. I don't know if people still do it. Take a piece of soap and tickle the rectum. Anybody familiar with that one?
Yes, so up in the country, well, we just do that still.
Yeah, so you know, take a sliver, you know, like take a soap and cut off a junk, you know, so like you have like a spear, like a little I don't know how to, well, a little sliver, a soap, and take and tickle. If you tickle the rectum, that has actually caused the muscles to contract rapidly. It's a reflex action. When something is pushed up in your rectum, it doesn't dilate the muscle, the rectal sphincter. It doesn't constrict, it actually dilates, right?
So, but all those things don't actually work for everybody.
I was now going to say that.
People,
you're very true.
They have people with Crohn's disease and IBS, and so those things wouldn't work for everybody.
I was thinking about a baby, but no, you're right. And one of the important, I'm glad you brought up that topic. Always remember, so like even when you find, I might talk on certain things, or even the knowledge that you get, as a nurse, as a medical practitioner, you will have to make the best decision based on the information that you have. Always remember that. So all you're doing is setting the table, but you have to decide, you know, what meal you're going to eat. And that's very, very true. It's just like with COVID, right? In terms of vaccine, should you get a vaccine or should you not get a vaccine? You know, all the information there. There are things on both sides, very good arguments on either side, but ultimately it rests with you. And I'm glad you bring it up. Always remember that one. Yes, you have the information, but the choice is yours. So thanks very much for bringing up that point. So don't say, well, so tell me to do that, or I learn it, you know, in this course, blah, blah, blah. Informed choice and recognize that that's what you do, you know, in terms of it. So you're quite right. If the person has some pre-existing condition, which could be exacerbated or made worse by using soap in the rectum, you wouldn't want to do that. If they have piles, rectal piles, or if they have Crohn's disease or something of that nature, yeah, you wouldn't want to do that, right? So always remember, make an informed choice. I was speaking from the perspective, however, of a non-Crohn diseased person, so I'll have to probably be a little bit more specific. And I'm talking about a baby. We're talking about in the range of less than 9 months or so. So I'll be a little more specific when I do speak in terms of that, but always remember to be aware or be respectful of every person or individual does have pre-existing conditions. So I don't know at what age they actually begin to diagnose Crohn's. I don't know if a child, you know, from probably so.
It's from 20. It's from 20 years old is diagnosed Crohn's disease or IBS.
Right. Irritable bowel syndrome.
Like
yeah. Right.
Yeah. So you have to be careful from a young age.
Quite so. Thanks for bringing that to my attention. Okay. So in this case, homeostasis. And what is homeostasis? Coming from the word homo meaning same and stasis meaning state, maintenance of the constant internal environment. So when things go out of whack in your body, in this case, consume lemon juice, right? Boom, that's a huge problem. So the body rectifies it, right? In terms of the neutralization, bicarbonate, it neutralizes it. Water and carbon dioxide produce. In terms of increasing the breathing rate, more carbon dioxide exhaled, and carbon dioxide is dissolved in the blood as carbonic acid. So you're giving off as well, excess acid is eliminated because you're breathing out more carbon dioxide. And the kidney, it excretes more hydrogen bound to buffers. So you're decreasing, here the problem is too much acid. From the kidney's perspective, is giving off hydrogen ions, so therefore it is lowering the acid. You begin to have rapid breathing. You're removing carbon dioxide, and so decreasing the probability of carbonic acid being formed, and then the administration of the bicarbonate neutralizes some of that acid. So these are solutions when it is you have too much hydrogen ions in the blood, or your blood becomes a little acidic. So they, as we mentioned before, 7.35, 7.45, you don't want it going outside of that range for any extended periods, or else you will be talking with the ancestors. So that's why it's very important that you have these mechanisms in the body that actually compensates and keeps it within that range. Okay, so macromolecules. With this, I just want to point out this. Just take note of the structures. You'll be responsible just for the structure of what it looks like. So if you're given images, let's say of carbohydrates, lipids, let's just say a diagram, you just should be able to tell them apart, right? So if I give you, let's say a diagram of this and a diagram of this, you should be able to tell the two apart, which one is a lipid and which one is a sugar. Prostaglandins, right, very important in the body itself, part of a steroids. Are steroids good things in your body? Yeah, some people, steroids are cures. What do they use steroids for? If it's given intravenously or intramuscularly. If it's given in an injection, what are steroids used for? It's used to control one thing. Some begins with I.
Inflammation.
What you're saying, it don't make sense. I teach because you all know everything. I am very good, but that's very good. Inflammation. So usually when something is associated with chronic inflammation, steroids are usually given. All right. Proteins, we're almost there. We have 3 more slides. Proteins are formed by a dehydration reaction. Here it is, you have 2 components that make up proteins. And what are the things that make up proteins? What are they called? It's a type of acid.
Amino acid.
How you know it's amino acid? Because it's right here. Always use your eyes. Very good. Amino acids, right? And how many, for our purposes, how many basic amino acids are there?
I'll guess and say 33.
A little, okay, less. That was a good guess, but no. But I applaud
about
you.
20.
What you're saying, you hit the nail. Ooh, well, Kavita wouldn't give you a wrong
20?
because they have discovered 2 more.
20.
So you're
23?
right. You're quite right. There are 2 and 3, depending on what research journal you look at. There are about 3 or 2 that are considered amino acid, new amino acids. But in terms of the literature, what do I mean in the literature? When you look at the nursing books, when you look at the medical books, you will see 20. So it is considered to be 20. However, within the last 10 years, they did discover 3 more, but they haven't fully incorporated them into the literature just yet. So for our intents and purposes, it's 20, but if you'd given me an answer of 22 or 23, I would give it to you correct. So there are 20 amino acids. Do you need to know the structure? Absolutely not. But just to appreciate when 2 amino acids come together, and why do they call it amino acids? Because here is an amino acid. On one side, you have an acid group, and on the other side, you have an amine group. NH2, amine, COOH. This is an acid group. And you have a dehydration reaction in which water is removed to form what is known as a amide linkage. So C double bond OOH, take off this OH, take off one of the H's from the amine group, and you're just left with NH, C double bond O, C double bond O, NH. And this linkage here is known as an amide linkage. All right, so that's all you have to know in terms of protein formation. Amino acids linked together by a amide linkage. And you just have it repeated over and over. And that's how you form a protein, also known as a polypeptide, right? But that's how proteins are formed. This protein, now protein comes in different shapes and forms. Remember, we did mention this last day, structure and function. There's a strong correlation between the two. What is this one here? We looked at this last week. It contains heme, right, which is the non-protein component, which is iron. And here you have the globin, which is the protein component. So together, the protein plus iron forms hemoglobin. And where do we find hemoglobin? What organ system does hemoglobin belong to?
Circulatory.
Cardiovascular.
I'm not mad at you for saying circulatory. Some books you'll actually would see it, but the correct one is really cardiovascular. Even though I have seen it in some anatomy book, you will see circulatory system. But the correct one is cardiovascular, because the cardiovascular embraces the circulatory system. And the other thing is, you could argue that the respiratory system and the lymphatic system, that they are both circulatory system. Because with the respiratory, your air is circulating, and with the lymphatic, you have lymph fluid that is circulating. So that's why, even though it is not totally incorrect to say circulatory system as it relates to blood, but it is more correct to say cardiovascular, because of the fact you could argue that both the respiratory and lymph systems are circulatory system. We good with that?
Yes, sir.
Okay, cool piece. But if it was, let's say if it was an exam and you put circulatory, would I give it to you wrong? Absolutely not. I would give it to you correct. Right, so this is a globular protein here, hemoglobin. Iron, very important. What symptom is usually shown when you don't have iron, or the iron content drops in your blood? What happens?
Anemia.
Anemia. Yes, very good. Anemic. And how would you raise your iron content?
I taken this thing, the red blood, if you know, the medication for it now, the hemoglobin medication.
Astafa. I think it's Astafa.
What you're saying? Yes, very good. Yes, right. So you take medication for it. Is there any natural things you could take? Are there any foods rich in iron?
Yes.
Fig, beef,
green leafy
Beets,
vegetables.
green leafy vegetable. When in doubt, green leafy vegetables. Give me some example of green leafy vegetables.
Kale.
Excuse me, kale. Hello.
Lettuce, cabbage.
Lettuce, cabbage,
bhaji.
kale, bhaji, dashing bush. All them things that green is good, yeah? So when you see iron content down, do take it. And piggybacking on what was said earlier, of course, it might work for everybody. So always be monitoring your iron content just to ensure, if it is you are anemic, that you know the iron content is where it's supposed to be. Okay, but that's very good there. So do remember that hemoglobin consists of a protein and iron together. And it's very important that you have the iron because it's folded in a particular way. You lose the iron, the folding changes, structure and function. Since the structure changes, the function of hemoglobin changes. So will it now be able to carry oxygen? Absolutely not. And that is why you have a problem with certain people, you know, when your iron content is low, hemoglobin will not form. The shape of the molecule changes. It doesn't do its job in terms of carrying oxygen. So always remember, keep your iron content up. Nucleotides and nucleotide function, I would just say one thing on that. All of those things are important for DNA. And we speak more to DNA when we look at inheritance. That's about the second to last topic you do when you're in SNF too. All right. So what did we look at today? Well, we looked at a number of things related to chemistry, specifically relating to chemistry or molecules important for life. So we started off by looking at the elements in the human body. We looked at the periodic table and then mentioned atom and charges, very important. Also, we threw in the notion of electrolytes, nothing more than carrying charges in the body, very important when it comes to the nervous system, which we'll speak to in our next two lessons in terms of generation of action potentials in the nervous system. Mentioned different types of bonding, covalent and ionic. Also spoke about hydrogen bonding in water, one of the unique properties, and this is because of the fact of the strong electronegative oxygen and weak hydrogen in terms of the charge distribution. So what you have when oxygen binds with two hydrogen, you have a partial negative charge on the oxygen, partial positive charge on the hydrogen. So this is why water is considered polar, because it has two separate charges. And now these can participate in other electrostatic attractive coming together with other water molecules. And this is known as hydrogen bonding, right? And that is what gives water a lot of its unique properties. We moved on from there. We spoke about anabolic and catabolic reactions. Anabolic, those are the ones that build up. Catabolic, they break down. And anabolic, think about a tree. It takes in carbon dioxide and water and synthesizes them into carbohydrates. Let me ask this last question there. What is the most efficient synthesizer of sugars in the world? It's a grass. Anybody knows what it is? A grass that makes sugar.
Sugarcane?
Thank you very much. We don't think about it, but sugarcane is a grass. It is a grass. It's very, very efficient at synthesizing or anabolism, taking carbon dioxide and water and making it into a complex carbohydrate, right, which we then consume. So we mentioned that. We also mentioned the importance of having a singular currency in the body, ATP, which can be utilized all over the body because of efficiency. So we drew the parallel with the ATM card or the links. And you know, wherever you go, there's one card and it could be used all over. Similarly in the body, 1 unit of energy, ATP, could be used by all the muscles. Very efficient because it's not complex. You wouldn't run out of, let's say, elbow moving ATP. You wouldn't run out of that. And then you have to study, okay, well, let me move my eyeball twitching muscle ATP and make some more elbow moving. No, there's one currency. So if it is you need any ATP in certain areas, it could be shuffled or moved via the blood, you know, to certain areas, right? In terms of glucose being moved to the cells via glycolysis, breaking down the sugars to produce ATP where needed. So it's a very efficient, always remember your body is a machine, very efficient machine. And that is why periodically it's good to get a good night's sleep, because when you sleep, that is when the machine is actually do some repairs and maintenance. After that, what did we go on to? We mentioned, of course, dehydration synthesis type reactions in which water is removed, and then you have the creation of carbohydrates. The very reaction in which sugars are made, carbohydrates, in which the plant takes carbon dioxide and water, combines them to form a carbohydrate, right? That is a synthesis type reaction. It's a very efficient reaction, right? And without it, right, we would not be able to get this complex carbohydrate, which is now taken in, and we do the reverse. We break it down, releasing carbon dioxide and water. Right? In a dehydration type reaction, we release the carbon dioxide and water. So water, of course, is given off into the atmosphere. There are, however, some animals. How do we know that water is produced as a result of respiration? Anybody can think of a very simple experiment you could do to prove that water is given off in the air that you breathe out? What could you do to prove it?
You can breathe out on a piece of glass. You will
Yeah.
see.
Anybody ever do that? Yeah, breathe out on a piece of glass. The glass is cool, and the water will condense on the glass. Right? So what is important to recognize? There are some animals, namely the kangaroo rat in Australia. It lives in the desert. Now remember, in the desert, you actually have a bit of a problem getting water. So what it does in terms of the machinery of the rat being so efficient, it actually extracts the water that it makes through when it breaks down food. So it doesn't when it breathes out. So if this kangaroo rat was to go in front of a mirror and breathe out, you wouldn't see any condensate or very little, if any. It has become, in terms of how the body has been adapted, it actually extracts that water. So somewhere along the respiratory tract, it condenses and is actually taken back into the body itself. So the air that the rat breathes out, the kangaroo rat in Australia, is very, very dry. So it makes use of that water, which is produced as a result of the catabolic reactions associated with breaking down food. It uses that water for its own consumption. Talk about the body being amazing. Then we mentioned, of course, the whole notion of the pH scale. Always remember, you don't want to get in a fight in the detergent aisle. Why? Because it has bleach there, and bleach it's very good at dehydrating. It dries you out very quickly. If it is thrown in its concentrated form on your skin, it will give you a burn. So you don't want that to happen. So please don't fight anybody in the detergent aisle. Go in the sweet section and let them pelt you with marshmallows. Then we spoke about homeostasis, what happens in terms of the blood bicarbonate level, of the use, of intravenous or orally consumed bicarbonates in terms of assisting with when you're taking too much acid. All right, so that is very good. The bicarbonate reacts with the acid to produce salt and water. It's a neutralization type reaction. On this topic, let me ask this question. If somebody consumes, well, I don't know if this, I don't think it still exists anymore, paraquat or gramazone. It's about other things which you could take, antifreeze, and they present to hospital. Sometimes we notice that, yes, they flush it out of the system and so on, but the person still dies subsequently. Anybody knows why? Why it is, even though they get it out of the system of the individual who drank it or whatever? Why does the person still die sometime 2 or 3 days later? Anybody have any
Because
idea?
it already damaged certain organs.
And which organ in particular it could do the most damage in, you think?
The lungs.
So
Okay, the lungs. Liver. Okay, what else?
Kidney.
What's the first organ you think it will hit? Stomach.
Oh.
Is it a problem if your stomach is messed up? If the lining of your stomach,
Yes.
yeah, that's a big problem. So in terms of nutrition, not going to happen. But not only the stomach, as you rightly say, all the other things, what you said is true, because of the fact, once it reaches the stomach, and when we do look at the organs in digestion, you'd look at that in SNF2, you would see the stomach has a lot of blood circulation around it. So imagine all of these, when you take in, be it paraquat or whatever, serious poison, it gets into the blood system very, very quickly because of the fact around your stomach has a lot of this, a huge blood supply associated with it, because that's how your body works. You take in nutrition, it is extracted in the stomach and is now distributed to the entire body. And as it goes to the body, be it sugars or other things, it's broken down at the level of the cell and taken in. So what happens if you take in poison? Yes, your liver will try its best to break it down, but sometimes if it's too much, you have a problem. And not only that, now the distribution system is being affected. You take it in your stomach, even if it gets past the stomach, which it probably does, right, past the pyloric sphincter, and it gets into now your small intestine, and then into your large intestine, it is messing it up, destroying the cells. So even though, that's why sometimes by the time they get you in, they might be able to get it all out, right? And how do they get it out of your stomach incidentally, even though you still have some in your stomach? Anybody? How do you get a poison out of your stomach? What do? They give you something, or they get out, or they pump it. Well, not only pump in your stomach, but they also pump something into your stomach to absorb the poison. Anybody know? It's
charcoal.
What kind? It's a particular kind of charcoal.
I can't remember the first name, the real name of the mobile.
It begins with A.
Activated charcoal.
Thank you. Activated charcoal, right? I remember there was where was he from? In San Fernando General. I want to say he's a Nigerian doctor back in the 90s. Dr. Adu, he formulated this substance what they would get down into the stomach consisting of activated charcoal and clay, right? And it was very good at absorbing the poison, but again, it all depended on when they got the person in. So getting it out is not an issue in that regard. But if it's already done its damage, well, you know, nothing they could really do, which is why sometimes you would see some persons who have consumed, you know, something exceedingly poisonous. Yes, they would come out of the hospital, but, you know, all their organ systems not working. So they die subsequent to that. Sorry to bring up something gloomy, but it goes with the territory of where we work in, yeah? Let's go forward. So we mentioned carbohydrates, complex sugars, the structures, if you would notice, carbohydrates, right? This is just the organic representation of it. Each of the points here is representative of a carbon, really. So, but this is what they look like. When you look at lipids, however, lipids have these like tails associated with them. And that is a major reason I can tell the difference between them. Right? Steroids, we mentioned that, prostaglandins, all of these are steroids. Steroids are very useful to control inflammation in the body. And the last one we looked at, protein shape, in terms of the function, this is hemoglobin, this is iron, the heme component, and it's very important that they both exist so that this will function properly. Okay, and that's it for the lecture. Let me just put a stop sharing here. Okay, y'all still there?
Yes, sir.
Yes, sir.
The
All right.
worksheet and the cavities, the drawing with the cavities.
Let's
the
have
review.
a look. Let's have a look. Okay. All right, so let's have a look at the worksheet. Let me